So this work happened at the High Performance Computing Lab at Northeastern University. It is a collaboration between myself as well as Alex Brick, Professor Gene Cooperman is the advisor and project initiator, and Sergey Baradas, who helped contribute to this as well. Thank you all for coming. So to get started here with the talk, I'll just give everyone an executive summary about what InfiniBand is, what is checkpoint restart, why does it matter, and why does it matter here at REcon. And to get this started, what is InfiniBand? InfiniBand is a switched fabric interconnect. It originated back in 1999. It was the result of work between Compaq, HP, IBM, Intel, Microsoft, and Sun. There were two competing projects up to that point that merged. At its heart, InfiniBand is a peripheral interconnect used as an L2 network. So the story is that originally it was designed to connect peripherals remotely. I think the basic use case they would have imagined was CPU talking to disk, remote disk. But in the world of supercomputing, they try and use commodity hardware as much as possible. So InfiniBand was very fast, very low latency, so they made it the network pretty much. And just to give you an idea of how prevalent it is, 43% of the top 500 supercomputers run InfiniBand, at least as of November of 2010. And the top 500 list is just what it sounds like. It's the 500 fastest supercomputers in the world. More importantly, though, to us at REcon, InfiniBand's presence in the cloud is growing, and it will only continue to grow as cloud providers feel pressured to promise better and better performance to their customers. This is important because in the world of supercomputing, most everything on the network is trusted. As far as I know, the security of InfiniBand has never been thoroughly pushed to its limits. Obviously, that's going to come to light as we see this hardware in the cloud. And just to give you an idea of the performance we're looking at, a Mellanox ConnectX adapter has a bandwidth of up to 40 gigabits a second. The latency can be less than 1 microsecond, and what I mean by latency is that for a very small message, a user-level process on one node can send it through the hardware, through the switch, and back to a user-level process on another node. And what's interesting about InfiniBand is that it allows for remote direct memory access, read and write. So you can directly manipulate the remote memory of another machine. Obviously, if you're going to allow that to happen, your implementation had better be secure. And in terms of playing with this at home, you can get low-end hardware that's used on eBay for less than $100. So just for reference, if you connect only 2 nodes to each other with no switch in the middle, if you connect only 2 nodes, you can connect directly together with no switch. So for about $100 on eBay, you could get 2 cards in a cable. And the common question, so just to address it right now, it's not related to and wholly unlike TCP sockets. So try very hard not to draw any parallels with what I talk about today between TCP. It will mislead you. This is a really simplistic diagram of such an InfiniBand system, but it gives the right idea of generally what you set up with these. You've got a fabric with switches in it, and you've got the consoles, the processor nodes, and the storage systems, and InfiniBand is the interconnect that brings all of that together. The next point here is that the reason our lab was interested in InfiniBand was to transparently checkpoint and restart high-performance computations that run with InfiniBand connections. Transparent checkpoint restart is the ability to save a running process to disk and later restart it as a new process. And this talk describes the first package able to transparently checkpoint software with active InfiniBand connections, and it's based off of the distributed multi-threaded checkpointer in our lab. So to the high-performance computing folks, the motivation for this is fault tolerance and debugging. Due to the massive number of components in some supercomputers, the mean time between failures is really low. So it's pretty common for a component to fail during the course of a 3-week or 3-month computation. So they want to have intermediate data saved so that they can restart the computation later instead of losing weeks of computing time. Debugging is also extremely valuable to them, as those programs turn out to be really hard to debug. So there's work in our lab to develop a reversible debugger, and once we have a complete InfiniBand checkpointing package, we can bring the two of those together. But the reason that this matters to us at REcon is because in the process of trying to transparently checkpoint and restart InfiniBand, we learned a lot about InfiniBand, and ultimately there's not a ton of documentation available, so all of that knowledge is valuable. Also, to transparently checkpoint and restart an InfiniBand program, we intercept all of the library calls and we play with the user data in the middle. In this case, it's wholly for innocent purposes, but you could essentially do whatever you wanted with the ability to intercept all the library calls. So InfiniBand does have an open specification, so why should we reverse engineer it? The first point is that the InfiniBand is quite sophisticated and it is proprietary. The InfiniBand network adapters actually have an iRISC CPU in them. And also, so the specification doesn't define an API, so it's not helpful in that regard. It essentially defines semantics of what an API should do. And for the de facto API that has arisen, the documentation is very sparse, and the man pages don't do a great job of painting a complete picture of this complicated system. The other tricky part of working with InfiniBand is that some state is held on the hardware. A lot of the valuable state is held on the hardware. There is some state in the drivers, and obviously this is mainly motivated by performance, that they would store as much as possible on the hardware. So generally what we do with this is we just experiment in the lab and we see what breaks and what works. So now the next part of the outline that I'm going to move on to is the story of reverse engineering InfiniBand. So we're going to look at the process of breaking down this technology so that we can transparently checkpoint and restart that. In this part of the talk, you're going to get a lot of valuable information and insight into the workings of InfiniBand. This is just a picture of an InfiniBand network adapter. Like I said, it is actually a fairly sophisticated piece of equipment. Formally, it's known as the host channel adapter. You'll commonly see that abbreviated as HCA, and Mellanox is one of the primary manufacturers. I only point that out because you'll probably see the name Mellanox come up a few times. Let's look now at one of the central concepts of InfiniBand, which is the remote direct memory access. So basically, two of these host channel adapters working together and communicating with each other on the network can access the memory on the other machines, and this is verified using keys. So what happens is the user process will give to the driver a virtual address that it wants to expose for remote access. This can be read or write. And the hardware, well, of course, the hardware doesn't know anything about virtual addresses. So the driver will first pin that section of memory into physical memory so it can't get swapped out. And then it'll give the hardware a mapping of the virtual address to the physical address. The hardware does maintain its own table. In the process, a key, which is used to verify access, is created, and that key also serves, as far as we can tell at least, as the mapping into the page table. That key obviously is going to become very important as it's the central verification mechanism. As long as we're talking about remote memory access, let's just talk about the other communication semantic that you'll see in InfiniBand, which is send and receive semantics. And that's your much more standard communication mechanism where you have two nodes wanting to talk to each other. So one node will post buffers that are ready to receive data. The other node will post a buffer that's ready to send data, and that data will then go over the network. Of course, the other node must have outstanding receive buffers available. This is not as powerful of a mechanism because there's no remote direct memory access. The other node has no concept of the other machine's physical memory. As we move in here explaining more about InfiniBand, I just want to bring up a quote real quick by Yogi Berra, very famous figure in Major League Baseball. He once told his players at spring training camp to pair off in threes. And the reason that I bring that up is because I just want you guys to remember that there are 3 queues involved in one end of a connection in InfiniBand. So these queues exist on the hardware. And what you've got what's referred to as the queue pair, which is the send and receive queue. And when a client wants to perform some work, it'll post requests to the hardware that go on the send and receive queue, and the requests are then processed. There's then a completion queue, which the hardware will put entries on when a work request is completed, and the client will then pull on to find out information. This, of course, means that InfiniBand's model is asynchronous. So you post work now, you ask later if it's been completed. In terms of checkpointing, this is a relevant point because we need to log everything to always know what state the queues are in on the hardware. And InfiniBand has 4 connection modes, and I'll go over these quick, but the most important one is reliable connection because that's the most commonly used one. Very similar to TCP. You have 2 nodes that have a set of queue pairs. Those queue pairs can only talk to each other, and the packets are guaranteed to arrive and arrive in order. There's unreliable connection, which is the same theory, except there's no guarantee the packets will arrive. There's also a reliable datagram mode. In datagram mode, basically, queue pairs can speak to any other queue pair on the network. They have to be authorized to do that, but they're not restricted to only speaking to one corresponding queue pair. This is a reliable mechanism, so this one's not actually implemented by hardware vendors. They spent a whole bunch of pages on the spec with this and never implemented it. And then there's unreliable datagram, which is very similar to UDP. Nothing's guaranteed to arrive in order. And just so you know, the reason reliable connection is used so much is because the whole point of unreliable datagram was it would perform faster, but the hardware vendors have so optimized the reliable connection path that it's actually faster in most cases, so that's what people use. Now, I'm going to bring up another point here that was relevant to checkpointing and will be relevant to us, which you'll see in a second, which is this packet sequence number. So to give a little bit of background, when I was trying to do the checkpointing, we have to shut down the InfiniBand connection before checkpoint and restart it after. Well, when we would restart the connection, nothing happened. All the packets rejected. I didn't know what was going on. I learned no idea what was going on. So I spent days digging around to try and find this out. And I finally found an interesting point here. So the user, there's a packet sequence number. That's just a 24-bit number that's used to actually verify that the packets are coming in order. It's very simple. That starting packet sequence number has to be specified by the verbs consumer. Well, in terms of checkpointing, after the checkpoint, we just use the same packet sequence number that the user program had specified before the checkpointing, because that seemed like the simplest thing. And it turns out that the PSNs the starting packet sequence number must be unique within a closed time frame, because the hardware actually remembers recent packet sequence numbers. So if you have a process running and you shut it down and then you start another process right after, it has a packet with sequence number that's close to the ones being used by the last process, the hardware thinks that those are stale packets from the old process and rejects them. This actually yields valuable insight into the history and origins of InfiniBand, though. If you think back to the fact that they were envisioning remote disk storage, if you were dealing with remote disk, and say you had a server crash or something, obviously you would want to reject stale packets because you don't want the disk to get into a bad state because some packets that were lost on the network for a while are suddenly showing up. And this is a tool that you all are familiar with, very useful in reverse engineering. This is one of the ways I even figured out the problem with the packet sequence numbers. Yes, you can analyze InfiniBand packets in Wireshark. At least for Mellanox, there is a tool provided by the hardware manufacturer that will dump the packets to a .pcat file. You can open them up with Wireshark and dissect them just as you would with any other packet. Anyone that might have interest in getting into InfiniBand, this is definitely going to be something that's going to make your life a lot easier. And let's just look at the layers here. of like the stack real quick, just because that, again, it shows something interesting about this. So at the top, there's the client code. Below that, there's an API library, a user space driver, and then there's a divergence, though. There's a kernel driver, and then there's also a path where the user space driver speaks directly to the host channel adapter. And actually what's going on here is that the page table has been changed to point at the PCI bus, so the user space driver can talk straight to the hardware. But this is great because this means that anyone that wants to talk directly to the InfiniBand hardware doesn't have to mess around with creating or modifying kernel drivers. You can do it straight from user space. And the short story here is that what they call slow path operations, which are things like creating a connection and managing it, things that don't happen a lot and don't need to be very fast, go through the kernel driver. And when something that needs to be very low latency, like a send or receive, is posted, you don't want the overhead of a context switch into the kernel, so they just talk directly to the host channel adapter through the page table. There is one point here that's also of interest. There's hardware protection. You can write to the PCI bus, you can't read from it, which is painful in two ways. In checkpointing, that's painful because we don't have an easy way to ask the hardware what its state is at checkpoint time. In reverse engineering, it's obviously not as fun because it's much nicer if we could just read straight out from the hardware. The question here that some of you may be able to look into, I'm not that much of a hardware person, is can you take the card and fiddle with the hardware a little bit to actually break the protections to try and prevent you from reading out of there. Moving on to the API. So I said there was no standard API defined in the spec, but there is a, quote, de facto API standard. It's provided by the OpenFabric's enterprise distribution, and their implementation of the InfiniBand verb spec is called libIB verbs. And the problem with the API is it's essentially a kernel space API exposed to user space. And what I mean by that is that it's not a pretty API at all. It's fairly complicated. Keep in mind it was mainly created, again, for remote peripheral use, so they didn't really have in mind your average person sitting down and just write up a quick application with this. And so people that want to know more about the API, though, there is a technical report I wrote that explains the overall gist of it, and that is at archive.org. You can get the URL off the slides if you download them after the conference. So now, at this point, just to paint a more complete picture of what goes on in creating an InfiniBand connection, though, let's look at a table of all the library calls that you would use. So first, you open a device, and the device will return a context. A context is just a structure that associates the various information associated with the connection. Then you create a protection domain, which isn't so much a security mechanism, it's more just a way of preventing, it's just a way of regulating what machines can talk to each other, and that's mainly to prevent erroneous traffic that could cause an annoying situation to debug. The critical part of this is where the memory region is registered, which I described a little bit earlier. So to review again, you give it a pointer to a virtual address, and it then pins the memory, gives the hardware a mapping of the virtual to the physical address, and it will create a key that can be used to verify access. Next, you'll create the completion queue, and then the queue pair, which consists of the send and receive queues. And then there's this modify QP call, and basically what you need to know about that is that you have to manually move the connection through the initialized state to a few other states until it's finally ready to go. Like I said, the API doesn't have a ton of frills to make your life easier. So now to move on to the next segment of the talk, I'm actually going to describe the solution to transparently and checkpointing and restarting the InfiniBand connections. Again, this is of interest outside of just high-performance computing because there is a lot of reverse engineering. This yields a lot of insight into InfiniBand, and the checkpoint restart mechanism actually provides tools that can be of interest to anyone trying to work with InfiniBand. To refresh everyone's memory here, let's go over the two main difficulties of checkpointing InfiniBand again. And the problems here are that there's a lot of state, such as the queues, stored on the hardware. We don't know what the state is at checkpoint time, but we have to know what the state is. So we have to solve that problem somehow. And this is another problem that is painful to checkpointing, actually extremely convenient to anyone wanting to reverse engineer this though. So the user space driver wraps the data structures returned to the user, and you can see the diagram here, which essentially explains what I'm saying, which is that all the drivers have their own internal data structures. So say for a queue pair, there's an internal data structure that represents the queue pair. There's also a public data structure common across all the user space drivers that the user program will actually see. Well, that public data structure is just a field embedded within the larger one. This is painful in terms of checkpointing because it means that we have to maintain the original structure, so some of the techniques that we could otherwise use to trick the client applications to otherwise not know that they're being checkpointed won't work. They're great for reverse engineering though, because if you want to play with the user space driver and you want to change things in it, you don't even need, a lot of cases, to change the source code. As long as you have the right header file, you can just do a cast, and you will then have a pointer to the beginning of the internal data structure, and then from a normal client application, you can essentially have your way with the user space driver. I suppose that in all research, it's worth pointing out what the alternative answers to the problem are, because obviously, when we haven't had this checkpointing package for so long, there must have been other solutions. And the first solution for a long time was that these people at the high performance computing labs would just write their own checkpointing code. Their programs would define their own checkpointing code. Moving a step forward here, so you've got OpenMPI, that's an inter-process communication library. And that connects all the individual processes in a large computation, and it can use various underlying network interfaces. Very common, and it'll run on top of InfiniBand. And just to put this in layman's terms, what I'm saying is that these supercomputer people don't want to deal with all the network connections. So they'll just write code on top of OpenMPI. OpenMPI will handle all of the dirty work for them. So Alex Brick in the audience, who was one of the collaborators on this, wrote a module that uses the core of DMTCP to actually checkpoint OpenMPI internally. And so OpenMPI quiesces the network at checkpoint time, and DMTCP will checkpoint the actual processes. And this is kind of a pain for Alex to do because OpenMPI is pretty complicated inside. The thing worth pointing out is the reason this can't handle all of the cases, and we've been doing the research work that we've been doing, is because there are many programs other than OpenMPI which interact natively with the InfiniBand API. So this is why the transparent checkpoint restart is desirable. Just to give an example, as long as I'm at it, like I said, this is still just a side note here, but just to give an example of like the things Alex had to deal with. The published interfaces of OpenMPI are well documented, the internals not so much. So the checkpointing infrastructure had previously only been used by a single third-party checkpointer, so there was another old package. So we wanted to add DMTCP to it to try and make it more up-to-date, more convenient. This revealed a lot of bugs. Just an example of some of the weirdness that happened. If DMTCP, when it was checkpointing, launched a child process, next thing you know, the message passing interface coordinator is running into an infinite loop, and this takes like days to figure out, and 2 lines of code later, you've got the fix. I guess that's a common story in this type of stuff. So let's look at the checkpointing architecture though, because this is actually of interest to most anyone here, because you could modify this for your own purposes. So to start off, this is just a normal diagram, a client application in a library. So to checkpoint it, well, basically DMTCP, our checkpointing package, sticks itself in the middle and intercepts all the calls. So how's this actually done? Well, we define all of the libIBverbs API symbols. We then use LD preload to make sure that we get loaded before the real library does. So we now own all of the API calls. So the API calls come to our code. Well, we can do whatever we want. We can change the data structures. We can make hidden changes to the connection that the client won't see. We can change the return values. And then to actually make everything work so that the client doesn't know what's going on, we'll use DLSim to resolve the real API function, the symbol to that, and then we can pass the functionality along to that so the real connection happens. And basically what we're doing internally is we're virtualizing the connection and we're logging all of the user actions that are going on. And those logs are important because post-checkpoint, to recreate the connection, we have to replay those logs to get the connection back to a previous state. But here's another diagram, again, just to show what I was saying, though, that you could take the checkpointing architecture and you could use it for anything you wanted, certainly far outside of checkpointing. So basically what we do is we have our internal wrapper where we have a pointer to the real data structure that the library is working with, and we then have a copy of that data structure that the client code sees. So the client code thinks it's seeing the real connection the whole time. In reality, it never sees the connection. It only talks to us. And like I said, you could change this to modify user data in any way, in such a way that the client program doesn't know that it's happening. Yeah, exactly. Nah, yeah, I was stepping around that one. Okay. So now I'll just show a quick demo of the checkpoint restart, just so everyone here can see the idea that we can, this basically allows us to kill a process halfway through execution and then restart it. So on the left there, the DMTCP coordinator is being started, and that manages all the different nodes on the network. And in these two, what's going on here is the demo program's being launched under control of the DMTCP checkpoint software, or rootkit as some in the audience may like to call that. So we're going to let it run for a second, and then I just hit the checkpoint command. So it's done with the checkpoint, so they're continuing execution again. And in a second, I'm going to kill it. All right, so it's dead. So at this point, we've killed it. We've got memory dumps with some other information that will allow us to bring this back up and rerun this program, which is going on right now. And just so you know, our checkpointing package supports all kinds of stuff, though, not just InfiniBand. You can also check, so you can have a screen session running with Emacs and Vim. You can checkpoint all of that and restart that on another computer. You could checkpoint NetHack or Rogue if you wanted to. You can do all kinds of various things for that for fun or convenience. And here we can see, so we've got these things restarted. You can see the connections recreated. They're resuming execution from halfway through the execution, and the user program is none the wiser. It doesn't even know that anything ever happened. Nah, sorry, I gotta get another mode. Okay. And the other practical application of this that might be of interest to folks here is a reversible debugger. So there's other students in our lab working to create a reversible debugger, and the principle is basically simple, that if you want to go back, if you have a checkpoint image from 100 instructions ago, and you want to go back in time 2 instructions, you just reload the checkpointing package and go forward 98 steps. This is obviously a lot harder than it sounds because things like threads and race conditions have to be deterministic. So that's a lot of work. But ultimately, the point is once we have a complete and full checkpointing package for InfiniBand, we can plug this into the reversible debugger. But even today, if you really wanted to, you could take the simple checkpointing package that we have, and you could build somewhat of a reversible debugger out of this. Basically, you just run the program under GDB, checkpoint the whole thing. Important point, yes, we can checkpoint GDB. So if you can checkpoint GDB, you just have a Python script that knows what to look for, where the bug is, and it just keeps shutting down and restarting GDB and doing a binary search over the course of program execution until it finds the spot where the bug actually happened. And moving on the outline here, I'm going to look at one last thing. I apologize here. I guess I went a little bit fast, so this talk's going to wrap up quicker than intended, but that's okay. But the last thing that I hope you all will like, so I mentioned earlier that there are these keys that are involved with the InfiniBand connection. So first, let's just look at what keys are used to authenticate. This is the primary authentication mechanism on the network to stop bad things from happening, our 64-bit keys. So first there's the M key, and the M key is used to authenticate subnet management datagrams. For example, this could be used to change the local identifier of a host channel adapter, but basically, if you have the M key, you can cause all kinds of havoc. You can reroute network traffic, do all kinds of fun stuff. So you would think that this M key would be very important. So I talked to one of the lead kernel guys on the InfiniBand stuff about the M key a little bit. And he said, well, we know that a 64-bit key is not really the greatest security mechanism. So I said, what's been done about that to this point? And the answer was, well, people have assumed that basically, since it's not that secure, people have spared themselves the time of setting it up and they don't use a key. They assume that everything on the network is trusted and that no one is going to start a rogue subnet manager, which means that if you're dealing with this case, if you can ever get into a network like that, you just got on one node, you can start your own subnet manager and you can then have free reign on the thing. Now obviously as this stuff starts popping up into the cloud, they're going to have to use the M key because they're going to have to secure it better. But the question is, how secure is that key really? And just to give you an example of another way that you can actually really easily beat the M key, there's a timeout mechanism here. So that if the subnet manager sets an M key on a node, if the subnet manager were to die, rather than having to restart the hardware to reset the M key, eventually the key just times out and it resets to an unmanaged state. So if you're on a network where this key's been set up, if you can just get the subnet manager to die and be patient, eventually all the nodes will be in unmanaged state. You launch your own subnet manager, you now control the network. There's also a P key, which is apparently a little bit obscure because of the way it was defined in the specification. I don't think it's used that commonly either. I think the idea was that you could take one fabric, though, and split it into multiple virtual networks so that you use the P key, so basically that in these partitions, no one can talk to a node that's not in its own partition. Like I said, I don't think it's used that much. And now we'll take a look at the keys that are probably of more interest to us. The first one is the Q key, and the Q key is used in the datagram queue pairs. So like I said, datagram queue pairs. So if you're dealing with a reliable connection, the Q key doesn't apply. But if you're dealing with a datagram QP, this is used to validate a remote sender's right to access the local queue pair. So this goes back to what I said about how, in theory, in a datagram, you can talk to anyone else on the network, but you don't really want to do that. So this is how they verify it. So if you leak a Q key, you can send erroneous messages to a queue pair on the network. I think the key that's the most powerful, though, is the R key. That's used in the RDMA read and write operations to authorize that the remote node has access to get to that memory. So the point is, if you can leak or guess the R key, and you can get some other pieces of information correct to forge a packet and get it on the network, you can have free will with another machine's memory to an extent. Probably only memory that was registered by that machine, but nonetheless, that means that regions that have been registered for other nodes that you're not supposed to be able to get to, you can now access. So we decided to look at the R key, see how secure it is. So our friend and very neighborly friend at REcon today, Travis Goodspeed, came up to Boston and spent a few days in the lab with us looking at the R key. I should point out, by the way, that since these keys are created by the hardware, the entropy that we're going to see here today is what we saw on our adapter in the lab. So your mileage will vary with other adapters, although I doubt it's been done all that much better because, like I said, just to frame this again, you have to remember the history of InfiniBand was that this was for supercomputers, high-performance computing applications. everyone on the network was trusted, these things weren't a big deal. So they haven't been tested, but now this stuff is popping up in the cloud. So all of a sudden we care about the keys because they have to be tested. So what is the deal with the R key? Well, the R key is 30, so basically the R key is produced in this format where you can split this up into bytes, A, B, C, D, E, F, and G, H. There's an example key there just so you can see what I mean. But we basically just kept running a program over and over and over that registered a new region when we looked at the key was. And it turns out that the entropy on the keys is very bad. The GH byte on the end there, it counts upwards slowly by 1. It increases by every circuit of the higher bytes. Those higher bytes, that's the AB byte, those cycle through 0, 0, 0, 8, 1, 0, etc. And basically what's happening there is that the B nibble is flipping its most significant bit while the other bits remain clear, and the A nibble is just counting up. So so for any given machine, this puts 13 bits into play, which means that on one machine, every 8,192 values, the keys repeat themselves. And not only do they repeat themselves about every 8,000 values, but if you know the current key, you know what the next key will be. It's guaranteed. The only problem here is that the CD and the EF bytes in the middle, those are constant per machine. They do change on the different machines though. However, there seems to be a very small amount of variation between those. So we think that whatever is seeding that value is some kind of probably like machine property or something. But basically, right now we don't know what's seeding that, but we don't think it'll be that hard to figure out. But even like I said, even if you don't know exactly how that gets seeded, it's not that hard to figure out what it'll be on any given machine. And even if you don't have it, that's still about 0.5 billion values in play. More importantly, like I said, the order of the keys is predictable. And there's also a virtual address that accompanies the R key, and that virtual address has an entropy of 17 bits for a 64-bit pointer. So this is where it starts to get a little bit painful because, you know, this R key by itself, even at 500 million values, isn't that bad. But now if you've got to guess a virtual address as well with 17 bits, they can start to get painful when you put all that together. But like I said, in theory that's not that bad though, because the other thing you got to remember, let's go back here, is that you can dump packets and you can load up Wireshark. So if you can actually get onto a few different nodes on the network, most likely from one of those nodes you can get a look at these packets and you can find out what virtual addresses are in play, and that's really going to narrow the field of what you have to work with there. Unfortunately, right now we don't, because we started that work, so you know that work's not been going on for very long. We don't have an exploit right now, but to look at where we got to go with this to get an exploit, we know that we can capture and analyze the packets with Wireshark. That's helpful. The problem is that the InfiniBand packets are created by the channel adapter hardware. Again, that's just a speed thing, right? Why have the kernel driver do it when you can have a piece of hardware that is designed to be extremely fast and specialized to that purpose do it? It also avoids, you know, any kind of overhead when you have to format the packets. So the problem is right now we don't have a mechanism to inject packets into the fabric. We need that to get an exploit to work. And the exploit I'm talking about, by the way, means we write a forged, basically we figure out the R key, the virtual address, because those aren't that hard to guess, forge a packet, stick it on the network. But like I said, there's hope yet, because we have this IB dump tool that hooks into some kind of debugging interfaces on the hardware that can read packets out. Well, most likely, you know, I don't know for sure, but I would imagine if you were to spend enough time reverse engineering this tool, you could figure out a way to use these debugging interfaces to inject packets back into the network. And for those of you that really like to decompile software and reverse engineer, there is hope as well. So for the majority of these binaries, you know, obviously they stripped all the symbols. If the symbols are stripped, it's obviously not a showstopper, it's just less convenient. But for some reason, and I think it was the OpenSUSE 10.3 binaries that they packaged, someone forgot to strip the symbols. So for anyone that wants to reverse engineer this, if you just get the right version, you don't even have to worry about the symbols. They'll all be there for you. And the other thing, like I said, the reason that I'm so excited to bring this part of the talk to REcon is because mostly in my short career, I'm only in my third year of college, I've been a software guy, and I'm getting more into hardware, but I'm not an expert. And I really think that outside of looking at this from the software world, if people that are really good at reverse engineering hardware, if they learn more about InfiniBand and they realize that they can get a hold of this stuff for pretty cheap and they understand how it works and what the API is, if they start digging in there with their oscilloscopes and all of this equipment and look at what's going on the hardware level, I think you can really start to learn a lot about this. And then you can apply that to what is the security implication on the cloud. In other words, I almost guarantee that after this stuff has been in the cloud for a while, eventually people will start to work out security issues that could be used to cause havoc on the cloud. So this is important research because a lot of very important data that people have is stored on the cloud. We want that to be secure. So if they're using InfiniBand, we want that to be tested much better than it has been. So I'm just going to, like I said, we're finishing about 15 minutes early, but I'm just going to give the conclusions of the talk again. InfiniBand is, so the problem with InfiniBand is that it stores data on the hardware, but we can intercept that by logging the library calls, and we can use that to provide a transparent checkpoint restart service. You can also use the checkpoint restart service for all kinds of other fun, though. The checkpointing package does this by virtualizing the connection and intercepts the API calls, so the user program thinks it sees the real connection when it doesn't. It's based off of DMTCP, which is checkpointing package out of our lab. And finally, so the source code's not publicly available yet. It will be. The only reason for that is because the stuff's like very alpha. So because we don't know that. I mean, checkpointing InfiniBand, this is we've only been doing this for 6 months, so it's very alpha. There's a lot of problems. I don't want to put that on the internet where a bunch of people are going to download it in the HPC land and wonder why it's not working. But if anyone here has a really striking interest in that, just shoot me an email. I try to be very neighborly with these things, more than happy to talk to people. So at this point, I can take questions. If there's no questions, I really appreciate you guys listening to this talk. I hope you learned something interesting about this.